Hello! In this video, I'm going to go over the answers to the exam practice worksheet on sampling. The first question is about sampling from this particular basenet, where the probability distributions depend on the values in the previous variable. So as we're told in this question, Susan first gets some number of dollars between 1 and 100 inclusive, and the number is chosen uniformly. When Susan has received the money, she must then give a portion to Jerry, who receives between 1 and S, where S is the amount that Susan received, dollars. And then Jerry subsequently gives some to Beatrice, again between 1 and J, where J is the amount that J received, and then Beatrice gives between 1 and B to Xavier. Our question then is, if you are Xavier and you receive $5 from Beatrice, then you want to know what is the probability that Susan received more than $50. You could represent this as a probability table. For example, the probability for Susan would be the possible values are 1, 2, 3, 4, etc. to 100, and each of these is probability 1 over 100. Similarly, the probability of Jerry given Susan would have a value for S, a value for J, and a probability, and Susan could have $1. And for each of these, the domain of Jerry would be 1, 2, 3, etc. to 100. And then the probability for Jerry receiving 1 if Susan got 1 is 1, because that's the only amount possible, and 0 for the others. But perhaps if Susan got $100, then Jerry would also have the domain of 100. And then the probability would be 1/100th each. So in this way you could, if you wanted, write out a probability table for this basenet, but it would be very big, and so we're not going to, because we don't need to. In order to actually solve a problem, we're going to do sampling. So for the first part, we're using prior sampling and generate these samples. In prior sampling, you generate samples through the entire basenet, starting from the parents and going through the children, and then you look at which samples correspond to your evidence. So here our evidence is x equals 5. So the first sample has the correct evidence, x equals 5, but the others don't. So we cannot use these samples in our prior sampling because they're not conditioned on the right thing, and so our estimate that S is greater than 50, since it was greater than 50 in our single sample, we're going to get a probability of 1. If we try to use likelihood weighting, we get a different set of samples, because in likelihood weighting you force the evidence to be correct. And we want to know what the weight of each of these samples is. So as a reminder, the weight of a sample is the product over all evidence variables. The product over the evidence variables of the probability of the evidence given the parent of the evidence variable. So here we only have one evidence variable, and that variable has only one parent. So if Beatrice, the parent of Xavier, has 10, that means that there is a probability of 1/10 for each value of x. So the probability of x equals 5 given b equals 10 is equal to 0.1, which is our weight. In our next problem, b equals 4, and since Beatrice can only give up to $4 to Xavier, Xavier could never receive $5. So the probability of x equals 5 given b equals 4 is 0, which is our weight. Again, b equals 10, x equals 5, so we get 0.1. And then b equals 5, x equals 5. So since Beatrice has $5, there is a 1/5 chance for every possible value of x between 1 and 5. So then we get 0.2. And for the last one, again, Beatrice only got $4, so this has a weight of 0. To figure out what the estimate of our query is, based on these samples, you add up the samples where s is greater than 50 and divide by the sum of all weights. So we have a s equals 52 with weight 0.1, and an s equals 87 with weight 0.1, and s equals 91 with weight 0. And on the bottom we have just all the weights, so 0.1 plus 0 plus 0.1 plus 0.2 plus 0. And this equals 0.2 over 0.4, which equals 1/2. So according to our likelihood weighting sampling, we get a probability of 1/2 for our query. In the next question, we have a simple Bayes net and probability tables. I'm going to fill in the joint distribution first, as the problem recommends. So for plus A plus B plus C, we have 2/3 times 1/2 times 1/2, then 2/3 times 1/2 times 1/2, which equals 1/6, etc. You just multiply the corresponding probabilities. Now we want to answer the following questions on different sampling techniques. So for samples 1 and 2, we're asked what is the probability that we'd have drawn the sample given the method. So in prior sampling, you first sample the most parent variable and then sample the next variables according to what you got in the previous variables. So for prior sampling, a probability of getting plus A plus B plus C would just be the joint of that variable, of this definition of the variables. And for sample 2, we'd get again the joint of plus A minus B minus C, which is also 1/6. In rejection sampling, you follow the same pattern as prior sampling, except that when you reach the evidence variable, if you sample it according to the evidence that you want, in this case plus B, you reject, or if you get the correct one, you keep going, but if you get the wrong one, you reject. This means that you'll never get a sample that has incorrect initialization of the evidence variable. So our probability of sample 2 is 0 because it's minus B. And also your probabilities of getting the correct ones are greater because you're not getting all the incorrect ones. So to calculate the probability for sample 1, it's just the probability of getting the joint, but then you divide it by the sum of the probabilities of only getting plus B. So we divide it by 1/6 plus 1/6 plus 1/18 plus 1/36, which equals 5/12. So in recap here, we reconditioned on probability of B equals B plus. So this is probability of plus A plus B plus C divided by the sum over all values of A and C of the probability of A plus B, C. Now for likelihood weighting, we decide ahead of time that b equals plus b, and then we only sample the other variables. So then the probability of drawing the sample is just the probability of drawing plus a, which is 2/3, times the probability of drawing plus c given plus a, which is a half, which equals 1/3. And in sample 2, since it's minus b again, we get a probability of 0. Now I want to use Gibbs sampling, and we initialize to all positive. And then we resample A, and then we resample C. So to calculate here is the probability of getting minus A, given that we already have decided on plus B and plus C. So this is just equal to the probability of minus A and plus B. I'm going to make that a better minus. Minus A plus B plus C divided by the sum over values of A of probability of A, B plus C. So this is equal to, going back to our joint distributions above, 1/18 divided by 1/18 plus 1/6. Which equals 1/4. Now we want to know the probability of getting plus C if you keep minus A and plus B constant, which is just equal to probability of plus C given minus A according to the Bayes-Nets rules. And in that case, that is 1/3. No, sorry, 2/3. And the last question is just asking, given that we picked this sampling order, what's the probability that we end up having picked both minus A and plus C in each sample? And so that's just the product of the two independent samplings. So we have 1/4 times 2/3 because we need to have picked minus A in the first resampling and plus C in the second resampling. So 1/4 times 2/3 equals 1/6.